Hi, everyone. Welcome. We will start momentarily. All right. Hi, this is Jim Tommaney. A little bit about the presentation. So DuckDB is kind of the highlights to see if you're interested in sticking around, but it's a fast database technology. It marks high on an ease of use characteristic, also flexible in its usage, and still some rough edges, and we'll kind of walk through all that. A little bit about my background. Currently with Databricks, working on data warehouse style queries in support of analytic workloads. I'll kind of jump back to the end. Previously, I worked with InfinityDB, helped to build out the column store technology that's currently growing and continuing to extend within the MariaDB ecosystem. My roles have always been performance focused, delivering customer solutions, talking about database technologies. DuckDB is the white paper that started kind of the effort. There's a CWI, Centrum Wiskunde in Informatica, which is a national research institute in the Netherlands. These two PhD students at the time, but now doctorates, are primary contributors into the technology. And if we take a look at the graphic to the right, there's embedded technology, which is, for example, SQLite, and then there's sort of traditional database technologies, Postgres, MySQL, MariaDB, Oracle, focused on OLTP workloads, and systems focused on analytic OLAP workloads. And the idea is that there's sort of a gap there. There's not really an embedded technology intended to deliver analytic workloads. And so that's kind of their thesis or their core idea that they want to work on. Mark and Hannes have primary contributors again. A little bit about SQLite. It has I'll leave with the last bullet, but it's 1.2 trillion installs reported because it's used virtually everywhere. So it's on your phone, it's on your laptop, runs in Firefox, Chrome, Safari. It's intended to be small, reliable, easy to use, open source, zero config, serverless, and these sorts of things. But SQLite, again, if we go back to the previous slide, is intended for OLTP style workloads and not necessarily analytic workloads. SQLite, so this is kind of the highlight. So DuckDB has many of the characteristics that SQLite does, but again, it's intended for different performance characteristics, so intended for analytics performance. But it is self-contained. It's actually installed as a single file. There's a couple different ways to use it. We'll walk through, but one of the ways the database itself is just a single file, and you can have portability with that file. It talks about multi-platform, and that actually applies into the database technology itself. So you could actually have the file created from a Windows environment can be deployed and used in a Linux environment. So the database itself is actually, they build DuckDB so that it runs on multiple platforms, and then you can have interoperability of the data itself. So you could actually move a file across environments and open it up without any problem. So it's intended to be simple to use. Is it a database? Yes, it's generally a database. So it has database behaviors that we're all familiar with, but some things differ significantly. So you don't do a start database command. It doesn't support or deal with concurrent transactions. HA is not kind of inside of its scope of responsibility, if you will. We'll do two different performance comparisons as we talk about the technology. One is just with SQLite, and this is definitely a workload that's analytics in flavor. So DBT3 is an open source variation of the TPCH benchmark. We're running just the queries and not any kind of load characteristics with scale factor 10 gigabytes, which is 60 million rows on the largest single fact table. Let's see. So the time to load was about 2,400 seconds, about 40 minutes with SQLite, and about 3 minutes with DuckDB. So significantly faster load time. And running the queries compared with DuckDB, there's you can run DuckDB with a single thread, which is also the model for SQLite, and you can run DuckDB with more than one thread. You can configure it to run 8, 16, 32, or more threads, and you get corresponding speed up. So I ran the test with a single thread and with 8 threads. Overall time is shown at the bottom here, and that's the about 2,600 seconds for SQLite. DuckDB with one thread was about 104 seconds, and DuckDB with 8 threads was about 32 seconds. Interestingly, the slow, so it's about 25x faster with one thread, 80x with 8 threads. Slowest query for DuckDB with 8 threads was about 5.4 seconds versus SQLite. They have 9 different queries that were over 100 seconds. And so clearly they differentiate in terms of performance versus SQLite. So they're successful in their mission, is in my estimation. This is the full, let me kind of go back here real quick to kind of show you what we're seeing here. So I basically charted like speed up. So the idea that query 1 was 29 times faster than DuckDB with one thread, and 217 times faster than DuckDB with 8 threads. And so, there's a full chart of all 22 queries involved. If we look at a little bit of detail, so first of all, the slide is truncated. So query 2 is 4,000 times faster with 8 threads, and I'm only showing up to 100 times faster. So the scale is actually truncated here. But query 1 and query 6 are the simplest queries, and we can kind of walk through the workloads on those. Query 1 is a scan of the largest fact table with a filter that does not exclude most rows. And query 6 is a scan of the largest fact table with a filter that does exclude most rows. And so those are the simplest ones, but it's significantly faster under those workloads. Other queries, like for example, query 20 and 22, it's about 2x faster with DuckDB, but not significantly faster than that. Additional metric coming out of this was, I basically tracked the memory utilization to both load and to run the queries. The SQLite was 28 gig, DuckDB was 12.3 gig. Modified taxicab queries. This is another benchmark. So there's Mark Litwinchik has a collection of benchmarks he's published that cross a wide variety of technology. So, Spark, there's OmniSci is it's a GPU-based database technology, but there's, probably a dozen different technologies he's benchmarked using a standard framework. I didn't go through his full process because there's significant transforms involved. I just did a simplified version of what he had done. And so my test case had at 1.03 billion instead of 1.1 billion. Part of his methodology was to take all of the raw data and transform it with, basically a single flat file, denormalized file that contained weather information associated with the trip, borough, which is sort of destination, source and destination information, and cab type was a key one. The cab type would be, a yellow cab, green cab, Uber, and so on. So I did not do those transforms. So this does differ between from his model, but the data volumes are close between the two. So 3 of the 4 queries run unchanged. The simplest query, I use vendor name or vendor ID instead of cab type. And so there's just that one's different. System run this on was an AWS instance with 16 cores, 32 hyper-threaded, 256 gigabytes memory. I ran this entirely in memory, and I used they have a read CSV auto functionality to load the data. And so the load was actually very simple. I just put it into the source files, ran that, and that actually detected the schema and defined the schema based on reading the CSV with the header. The queries themselves, there's I use two variants on the first one, but from top to bottom, it's a single group by with a count, a single group by with an average. The next one is grouping by 2 columns, including an extract of year. And the final one is grouping by 3 columns, including extract of year and something about the distance. And because distance is highly variable, this actually has a higher number of distinct group by buckets than the previous operations. And this is metrics associated with running this test. I ran it with 1, 2, 4, 6, 8, 12, 16, 24, and 32 cores enabled for this system. And what we see is a couple things coming out of this slide. So first of all, we see very strong linear scalability through 16 cores for 3 of the 4 queries. And I'll talk about the top one on the graph here. And then we actually see kind of a different slope when you get to between 16 and 32. That's actually expected behavior because these aren't physical cores, but hyper-threaded cores. And so they don't have the same utility. So one of the characteristics of vector technologies like DuckDB, and there are other systems that have vector technologies, is actually hyper-threading has a smaller net benefit because the vectorization actually lets the CPU use the core technology more efficiently. And so this is actually a typical behavior. There is some nonlinear scaling as you go beyond 16 with the query that runs at 3.6 seconds. That's actually kind of an issue, and they've got that tracked. It actually might be fixed by now, but I haven't had a chance to come back and retest that. But elapsed time 0.28 seconds, 0.4, 0.7, 8, and 3.6. So we can do kind of just a very rough comparison with what Mark has posted on his sites, but the time is at 16 cores. It shows strong performance. I grabbed just the timings for the number 11 slot on there, and so it appears to be somewhere in the top 10. But again, not an apples to apples comparison in this. But it does seem has good performance and across these use cases. Discussion about the word embedded. And so it's not a client server process, and that's a significant distinction that anyone using the system would need to be aware of. Instead of a process connecting, and I'll use the example of Python connecting to a DuckDB database. Instead of 2 processes running side by side, and if you looked at top, you might see utilization for the database and utilization for Python process go up and down depending on the workloads. What happens is actually DuckDB is running inside Python in this example, and so that's just a fundamentally different use case. And the example, my graphics here, talk about using Python, but you can also run the DuckDB from a command line interface. It actually shares the SQLite command line interface, so it looks and behaves like SQLite from that standpoint. Python, R, C, C++, Java are all natively supported APIs that DuckDB, that team delivers, and there's third-party APIs that have been created, and so there is an ecosystem beyond just what the team, the core team is doing. Okay, so embedded is definitely a simpler model and offers ability to be more powerful. But one of the things that's interesting is there's no process-to-process overhead, so you're not having to serialize data and deserialize it, moving from the database to the client. Instead, all that happens basically in shared memory structures. And then the other part that's interesting is actually fully parallel inside DuckDB. So you can have a single threaded application and it makes an SQL call, and that SQL call is now parallel operation. And so those are kind of an interesting characteristic of the system. Again, the example here uses Python, but any of the other APIs, C, C++, C# in the extended environment are all possible. A little bit of discussion about serverless. So you'll see 3 syntax statements here: import DuckDB, cursor equals DuckDB.connect, database equals memory, read only equals false. And I'll talk through the details there. And then results equals cursor.execute, select count star from line item. So in this scenario, basically the first 2 statements don't allocate any processes or consume any significant, don't allocate any memory or consume any significant CPU utilization. They're just setting things up. And then we do use resources in support of running that query, but that's the idea of serverless, is that you don't pre-allocate and pre-populate a process to run. Instead, it's sort of on demand. And so, for example, if you ran this query once per hour, the remaining time intervals on that device or wherever you're running this are not going to have any dedicated memory or CPU in support of this. There's some exceptions to that. It does do caching behaviors, and so it would cache results here. So it could have memory carry over there, but you could also close it down and reopen it again as well to manage that process. So basically, it allows for the developer to create their own behaviors. Let's see, limited shared access. So this is kind of one of the fundamental limitations and differences, is that when you open the database, it's going to be read only equals false, which means that you can write, or read only equals true, which means that it's a read only access. And there's a fundamental limitation when you're dealing with this file. You can only have one master, if you will, that controls this. So you don't have full database behaviors, if you will, in terms of accessing the file. And even within the scope of a single process, you can have one connection, one thread, read write, and you can have other threads read only within that process. You can do database equals memory. Just the behavior there, everyone should understand that it's ephemeral, it's temporary. When you stop the process, the data is gone. So it's just a different usage that's possible. One of the characteristics, just to reiterate here, is that the way this is set up is that database is just a single file. And so it has the utility that you can close the process and copy the file somewhere else, either for HA purposes or to copy it for transportation to external system or reuse. Installation is very simple. They've got a full list of installs on all their supported environments: Mac OS, Linux, Windows. There's actually a third party who's run this on a Raspberry Pi, which is a small device with a very small footprint. So they've got a modified version that runs there. So a little bit of jump into the code constructs, but import. The summary is at the bottom right here, but it's import DuckDB, connect. You create your tables and you run your query. As we walk through kind of the longer text in the middle, there's import DuckDB, connect memory, database equals memory, read only equals false. Create table as select from read underscore CSV, auto, and then there's a syntax there. So I point to the file that I'm reading from, header equals 1, auto detect equals 1. So that's basically going to define the schema for me. And then you can just run the query. So this is sort of the hello world example. I just happened to grab a Kaggle use case. The country vaccination CSV is a Kaggle data set. And I didn't need to do anything in terms of defining schema. So there's it's very easy to use in that standpoint. This is probably the most interesting or kind of relevant slide in the deck that gives you an idea about the different ways to use DuckDB. So we loaded a data set that was 5.9 million rows, 2 gigabytes. We can load it to memory, we can load it to file, or you can do neither. And I'll walk through that one. But the first one is just load into memory, and the 2 gig, the 5.9 million rows loads in about 10 seconds into memory. It's about 14 seconds to persist it into a tweets.db file. And then the third one, the syntax at the bottom is copy. So it has copy to tweet under results.parquet, format parquet. And then internally that says select star from read CSV auto. And so that's a streaming operation. And I'll talk about that in well. So it takes slightly longer because it's reading and writing and doing some transforms from a CSV format to a Parquet format. And this is kind of the visual representation of what's going on here. Read CSV using the auto syntax. It stores data in a vector memory and does a copy to the Parquet format. For a scalar transform like this example, which is just reading files, we're not like doing any group by, we're not doing any set operations in terms of ordering those. The memory cost is actually very small. It just loads into a vector, does the transform, and writes back out. And it can be done with a very small memory footprint to do that. And you can actually do this and join to a dimension table. For example, if you wanted to replace an ID with a fixed value, you can join to a dimension table, and the memory cost is basically the vector size plus the size of the dimension tables. You could do other things where the sort by, if you did a sort by operation, then that's going to have a fundamentally different internal memory utilization. So you could say the first two are probably very clean streaming operations, and the third one, you'd have to understand the memory required to execute the sort or some other group by operation. Some notes on non-compression. Right now, this is one of the roadmap items. So source data is about 2 gig. The tweets.db is actually larger than the source data. But if you transform to the results.parquet, it be smaller. Quick check here. Okay, so from this standpoint, we'll talk about performance characteristics. So you can use Parquet file. You can actually read from Parquet and write to Parquet, or read from Parquet, or read from 2 Parquet files, and join those as if it was database files. So it's actually highly flexible in that use case. The trade-off there is that you're managing individual files instead of a single database file. Join order is not yet kind of defined for you. So you'd want to think large table to small table from left to right after adjusting for filter values. Index is not needed. Double is not as fast double is much faster than integer. That's kind of a current situation. I've run this scaling up to 92 cores with near linear performance, and so it's very strong there. The syntax to tune your parallelization. Some notes on reliability. It's pre-GA. It's version 0.2.6. From the team's effort, they actually built significant test case first, and now they're extending functionality second. And so they understand the requirements for stability and predictability for an embedded system is fundamentally different than potentially other systems. And so they have been working on that problem from the start. From my usage, it has generally very predictable behaviors, but as always, test before you use. A little bit of a background slide. Just the team that built this is actually this CWI Institute was involved with building MonetDB and VectorWise. They talk about the technologies they use with this y_DuckDB place, but they talk about building on top of existing technologies. Architecture overview, vector column and parallel are core to for many systems for efficient CPU utilization. They've got very good thread scheduling and parallelization with what they call a vector volcano model. Don't have enough time to talk through that detail. Let's see, data skipping. So these components here, these features of their architecture are actually kind of why they do well in the TPCH benchmark we did, or the DBT3 benchmark we discussed earlier. So they have data skipping enabled for many scenarios, highly effective query transformations, They have the ability to take a predicate and push it from a subquery to outer query or back and forth, and they have a highly tuned hash aggregation behavior. Roadmap items, data compression, and that's related to the dictionary native operations. So they want to be able to basically have a dictionary in support of, for example, string operations, and be able to operate on the basically dictionary itself. Performance opportunity with double versus integer, their subquery scalability. Late materialization, they currently don't really do late materialization. They'll do, if you only reference like 3 columns, for example, out of the table, it'll limit the query to that. But if you had, let's say, a really tight filter on column 1 and projections of columns 2, 3, 4, it'll actually it'll actually access columns 1 through 4 and then filter first, and then the optimizer as well. So generally, yes, it is a database with these limitations: no concurrent writes from separate threads, no real backup model. That's up to you. The serverless case is definitely interesting, and I would say that the ease of use is actually atypical from traditional database systems. So there is a parameter you can use to constrain memory to a certain boundary, but that's I've actually never used that. It's not really necessary. It actually reads, understands your memory utilization and will find a useful value. The only thing I've messed with was the thread parallelization because I wanted to test that. Some limitations. If you have a database size larger than available memory, there's some challenges around that. So, for example, if you had 20 tables that were 10 gig each, you could access one of those at a time in 10 to 15 gig of memory. But if you only had 30 gig memory, you can't really deal with a data set that's larger than memory. It is, row by row loading model will be slower. Compression still on roadmap, and concurrent write is a fundamental limitation. This is kind of the questions and discussions, and I'm going to jump into the series of questions that we see. Okay. Yeah, so there's a question about the DuckDB. So you can, so you could be processing it with, you could process it, Python process, and you want to kind of like look at the file. You could actually just run the command line operation and do basically Postgres operations to peek at SQLite Postgres that's compatible. And you can use that operation to describe the table, to get counts, to do, if you wanted to prototype your queries before you got there, you could do that as well. Other questions for anybody? Right, I think we're right at the time limit, so we'll see if there's any questions come in. I'm certainly available to follow up after this if anyone wants to reach out with additional questions. There's a question about who are the early adopters, and I don't have the full list. If you visit duckdb.org, they actually talk about, they've got a wall of tweets. People who have looked at the technology. They've got, so these are individuals that actually work for CWI, but their work in some cases can be sponsored by a corporate entity. And I don't have the specific name, but my understanding is that they're one of the sponsors, actually a very large company we would all recognize, but I'll let them provide that information. I don't know of any classic use case that I can point to right now in terms of adoption.